coherent deduction or synchronous deduction. So here we learned here that the phase of the carrier is important. That is the phase of the carrier signal that is at the transmitter side and the locally generated carrier signal should match. So this phase difference phi, it should be 0 degrees in this equation. So otherwise we cannot recover the original information properly. So the next method is called Costas loop. So in this method we are going to match the phase of both the signals, that is the carrier signal at the transmitter side and at the receiver side. The phase difference is going to be 0. So we are going to correct the phase errors in the system by using a voltage control oscillator. So Costas loop is used to make both the carrier signal used for the DSBSC modulation, that is at the transmitter side, and the locally generated signal in phase. So we are going to make both the signals in phase, and ideally we are going to correct any phase errors if any. So here we are using two product modulators similar to the previous method. We are using a product modulator and a low pass filter. So DSBSC waveform is given as input to the both the product modulators, and the other input to the product modulator is from the voltage control oscillator. That is here we are generating a local carrier. So on the receiver side we are generating a carrier signal from this oscillator, but the difference between a local oscillator and the voltage control oscillator is we are going to feed a DC input from this phase discriminator. We are going to feed a DC input signal to this VCO or a voltage control oscillator. So based on this DC input, this oscillator is going to produce the carrier frequency. So because of this, we can correct the phase errors, if any, that is between this transmitted carrier waveform and the locally generated carrier waveform. So now this product modulator output is passed to a low pass filter, and this output is AC by 2 cos phi into M of t. So this is given as input to this phase discriminator, and other product modulator on the other side. So here this is in phase and this is quadrature. So here we are shifting the phase of the oscillator signal by 90 degrees, and this is fed as input to the other modulator, product modulator. So this is again filtered. So this output, the phase shifted version, here it is AC by 2 sin phi into M of t. So these two signals are given as input to this phase discriminator. So because of this, the phase errors are corrected from the DC output that is obtained at the output of the phase discriminator. So this is going to correct the oscillator, that is the locally generated carrier from the VCU. So based on this, this is like a loop. It will keep on going. So when this phase discriminator will produce a 0 DC output, then VCO will give a proper phase. Okay, until that, this loop will keep on continuing where the phase is getting matched. Till the phase of both the carrier waveforms are matched, this loop will keep continuing. So let us see the analysis. So Costas loop consists of two product modulators with common input S of t, which is DSBSC wave. The other input for both the product modulators is taken from the voltage control oscillator. So with the other product modulator, input is 90 degree phase shifted. So upper path is called in phase coherent deduction I channel, and the lower path it's called as quadrature phase coherent deduction or the Q channel, because we are shifting the phase of the carrier by 90 degree. So this is Q channel, this is I channel. So this PD and VCO is used to correct the phase errors. This phase discriminator and VCO, voltage control oscillator, are mainly for the phase error correction. So if you see the analysis, so this is the input waveform S of t, which is AC cos 2 pi FCT into M of t. So this is our DSBSC waveform, that is carrier waveform multiplied with the message waveform, and here we have suppressed the carrier. So the output of the voltage control oscillator is cos 2 pi FCT plus phi. So let us take this output as C1 of t, which is cos 2 pi FCT plus phi. So now these are the two inputs to the product modulator 1. So we are going to multiply both these inputs. So this output of VCO is applied as carrier input of the upper product modulator for the I channel. The output of the upper product modulator is nothing but product of S of t into C1 of t. So let us take it as V1 of t, which is the output of the product modulator I in channel, in phase channel product modulator. So this output we are going to multiply these two equations. Now here again we will apply trigonometric identity. So this is cos into cos. So after expanding, we have to pass it through a low pass filter. So this low pass filter is going to filter the high frequency components. So this will be, so after you expand, this is cos phi m of t plus cos 4 pi fct plus phi into m of t. So after you expand. And now after filtering, so we are going to filter the high frequency elements. So only this AC by 2 cos phi m of t will be at the output of the low pass filter. So this will be the output of the low pass filter. So let us take it as V naught 1 of t, which is AC by 2 cos phi into m of t. So now you can see here this is sine of 2 pi fct plus phi. This will be the other input. So let us take it as C2 of t. So now this will be multiplied with the DSBSC waveform. So now what will be the output of the product modulator? After you multiply with S of t, let us take the output of product modulator 2 as B2 of t. So this is S of t into C2 of t. S of t is the DSBSC input. So you have to expand using the trigonometric identity. So this is cos into sine. So now this is given as input to the low pass filter. So this low pass filter will filter the high frequency components. That is 4 pi fct component will be removed. And finally we have AC by 2 into sine phi into m of t. So this will be the output of the filter. So let us take it as V naught 2 of t. So this is what is mentioned in the block diagram, the outputs of the two low pass filters. So these are fed as input to the phase discriminator. So now, so this output is 90-degree phase, has a phase 90-degree phase difference with the output of the upper low pass filter. These outputs are applied as inputs to the phase discriminator. Based on the phase difference between these two signals, phase discriminator produces a DC control signal. So this output of the phase discriminator is a DC control signal, which will control the VCO. So based on this input, the output of the VCO, the carrier frequency is dependent on the DC input signal from this PD. So this signal is applied as input to VCO to correct the phase errors in the VCO output. When PD output is 0, there is no need to correct the local oscillator. So till that, this loop will keep on continuing until the phase errors are corrected. So this system will automatically correct the phase errors. So therefore, the carrier signal used at the transmitter end and the locally generated carrier are in phase. Through this method, we can correct the phase errors. So the third method is called the squaring loop. So this is one more method. We can recover the carrier signal. So from the DSBSC waveform, this is just for the carrier recovery. So in the previous methods, we are going to recover the message. So here in this squaring loop, we are going to recover the carrier waveform. So the recovered carrier signal is used in the coherent detection process. So this carrier, we can use it at the receiver side for the coherent detection. So through the transmitted waveform, we are going to recover the carrier signal. So that carrier signal can be used for the detection process, the synchronous or the coherent detection. Because if you use the same carrier, the phase errors can be eliminated. So here, this S of t, which is the DSBSC waveform, is applied to a squarer. So here it is just squared. So S of t is becoming S square of t. So this is given to a narrow bandpass filter. And so this filter output is given to a PLL, that is phase lock loop. So this PLL is basically again to correct any frequency or any phase errors. And this is given as input to frequency divider. So this frequency divider, it will just divide the frequency by 2. Finally, we obtain a carrier frequency of FC. So let us see the analysis. So through this block diagram, initially the output of the squarer is y of t, which is s square of t. We are just squaring the DSBSC waveform. So this output is just a square, and we are giving it to a filter, narrow bandpass filter. So this becomes AC square by 2. So this cos square is again, we are using one more trigonometric identity here. So we have 1 plus cos. So you know that cos square theta is 1 plus cos 2 theta. So this identity you have learned, right? 1 plus cos 2 theta by 2. So this becomes AC square by 2 m square of t into 1 plus cos 2 of 2 pi fct. So it becomes 4 pi fct. So the output of the square is given to a narrow bandpass filter, which is centered at 4 pi fc. So that it is going to filter only this carrier component. So this output of the filter is AC square m square of t into cos 4 pi fct. So this first term, this one term is getting removed. So we are left with only this 4 pi fct term. So this output is given to a PLL to provide a constant frequency signal. So this is just for the frequency or the phase error correction. So any drift in the frequency is corrected by the error signal generated by the low pass filter. So this output of the VCO is connected to a frequency divider to get cos 2 pi fct. So after you divide the frequency by 2, we are going to get exactly cos 2 pi fct. So this is just for recovering the carrier frequency. So this is called as a squaring loop.